email. Okay, so
just one moment, Alberto. One moment.
Oh, sorry.
Good morning, everybody. Welcome to a new webinar for my project. So today we are following with the presentation of use cases, and we have two presentations. So first we have one presentation from Adalberto Perez from KTH, and he's going to present the NEK turbulence simulation, with NEK5000. So please, you can send the question through the chat, and you can ask questions also you want to use voice at the end of the presentation. Okay, so thank you, Alberto. Give you the floor and you can start.
Thank you, Jesus, for a nice introduction. So thank you also the participants for coming. My name is Alberto Perez, as Jesus said. I am part of the Department of Engineering Mechanics in KTH in Stockholm. And as it has been said, I'm going to talk about turbulence simulations with NEK5000. So for context, before we actually get into the code, just so you are able to see some of the challenges that we have when we simulate turbulence, I'm going to explain a little bit of it first. That would be the first step. So let me see this slide. It's not moving. Yes. So turbulence, right? I guess this is a word that we all know. And, probably the first thing that comes to your mind when you think of turbulence is what you experience when you are traveling. And, it's been depicted here in a number of movies, very good ones. But then it is something that, let's say, everyone knows, at least this definition of turbulence, but this is not exactly what we mean when we say turbulence simulations with NEK5000. What we mean is actually, as a turbulence, what we consider as a turbulence is a complex, nonlinear, multi-scale phenomenon of irregular and seemingly random motion of a fluid, right? So we have a fluid such as air that is moving. We call this a flow. And when the flow is moving with certain characteristics, then we deem it as a turbulent flow. And then this is what we are actually interested in. So why should we, as a community, not only the CFD community, but in general, why should we care about turbulence? Well, it turns out that turbulence is mostly responsible for the high fuel consumption of air, land, sea transportation systems. So, of course, this means that we care about it because of money, but also, of course, because, more fuel consumption, we want to reduce fuel consumption, so we are more ecological and all this. But I would say turbulence is not only important for transportation systems, it's also important for example, pipelines. Here you see a small picture. Like a lot of the energy that is used in industry is transporting fluid through pipelines. And most of these regimes, like most of this transportation is done in the turbulent regime, right? So we want to control turbulence. We want to reduce it to improve energy efficiency of our systems. So here we see one slide, a little bit more of motivation of why turbulence. Here we see the evolution of the kilometers per person that a person travels per day, as the year progresses. And then we see that it is increasing, right? And that this trend still continues today. And, we need to be efficient with these systems so we stop consuming more and more fuel. So I would say that's a very big motivation, right? So solutions of turbulence by means of numerical methods, it started about 100 years ago. Back then, we didn't have MPI, we had people, so people were solving the equations by hand. But then it was started here by Lewis Fry Richardson for weather predictions in that case. Actually, turbulence is also relevant for weather prediction. But then one particular thing that I want to mention, and that in the end becomes a big computational and storage challenge, is this. If you see these pictures here, you see on the left, let's say a zoom out picture of the flow coming out of a volcano. And then you see that the flow has some structures to it, right? You can see that there's some structure to the flow, but then if you zoom in, you will see that in the small scale, we also have these structures. So we have large structures in turbulence, and then we have small structures. This means that if we want to solve this in computers, we usually need some discretization. We need a mesh that is big enough to solve the large structures, but it also needs to be able to solve these smaller structures, so it needs to be a very fine mesh. And then here is where the computational challenge comes, and we need a lot of points. So keeping with the transportation topic, if we, for example, want to do a simulation And here I mean a direct numerical simulation, so we don't use models for turbulence. If we want to do a simulation of a plane by year 2010, this is not really possible. It's not feasible, at least. So instead, what could be done is a simulation of a flat plate of the top part of a wing, for example, right? Which would still give some information to characterize turbulence. So if this is done, then what we see in the results is just what I was mentioning, that if we are looking at it from afar, let's say we see the large scales, but then if we start zooming in, we will see that the closer we get, we still are seeing these structures that are very small, but again, that we need, right? And here there's a visualization of turbulence where we see these structures happening in the domain. And again, I have said this many times, but I keep saying it. We need our mesh to be able to solve these small structures because they are very important for the turbulence, for the friction and all these things that produce in the end drag and air resistance. So what happens in the end is that, well, this was the largest simulation of a turbulent boundary layer in 2010. And, you know, we needed, well, people that did it, I wasn't here yet, needed 7.5 billion grid points. This is a lot. Then consider that, you know, if we want to store data in double precision and we need to store more than one velocity field, then this becomes not only a computational challenge, but it's also a storage problem, right? Like if we want to save all the data, it's simply not feasible. It's not possible. We cannot do it. Yes, so that introduction was a little bit of turbulence on why it is important and why is it challenging to do computationally, right? So then we can actually start talking about the code. So the code that we use is NEK5000, which is a spectral element code. It was developed by Paul Fisher in Argonne National Lab in USA. It's written mainly in Fortran 77. It has some C, and it's a pure MPI application. It won the Gordon Bell Prize in 1999, and it's been used by a number of European projects, not only at Meyer, but also in Exaflow, Accelerat, among others. And one characteristic is that it scales very well it's been tested to up to 1 million ranks, and actually that's why it won the Gordon Bell Prize. So, to explain to you a little bit the concept of spectral method, I have this slide here that perhaps you are familiar with finite element methods, and if not, then I will just explain to you very briefly. It is a low order method that allows to mesh like very complex geometries. Like for example, here we have a heart geometry, and it's possible to mesh this, but again, it's typically low order. On the other hand, we have the spectral methods, that are considered typical is an infinite order discretization. The more points you add, the higher the order you get of the discretization. But then you are limited to very simple geometries. Here we have a cube or a rectangle in 3D, that sort of geometries. So then the whole idea of the spectral element method is to combine these two to get some sort of a compromise. Discretize the geometry in some elements. Here you see these big squares that are have bold edges, and then locally inside these elements, then we can add a spectral discretization that gives us, in theory, a locally infinite order, right? So this allows us to retain a high order discretization while still giving us a little bit of flexibility with the geometry that we can mesh. And why high order? Why don't we just use finite element methods? Well, the thing is that here this aims to explain that, and here we see a case called a convecting cone, and here we see the exact solution on the top left, and we see how a solution can a solution by numerical methods looks for different orders. So you see that here, for the higher order, as would be expected, we have a solution that closely resembles the exact one. But also, we do this by keeping a lower number of elements, and in the end, sort of the same or even lower number of grid points. So, you know, it is a very good thing if we care a lot about accuracy, which we do in turbulence. Okay, so having talked a little bit about the method, then I just have one slide showing to you what we are solving, and this is important also because this will allow us to see how is the workload in the application. So here we have the incompressible Navier-Stokes equation. These are continuous in space and time. We have on top the momentum equation, and here we have the continuity equation. Right? So these are continuous equations. To solve it in my computer, we need to discretize them. So I first will show you how they are discretized in time. So basically we have a time interval and we discretize into a series of time steps. Right? Once we have done this, then to time integrate these equations, what we need to do in every time step is evaluate some terms that you know from solutions before, like from previous time steps. Then solve an elliptic equation, a Poisson equation for the pressure, that this equation is actually very stiff, and this is what generates more stiffness in the numerical method. And then solve a Helmholtz equation for the velocity, right? So those 3 steps, basically, you could summarize. Well, there's a lot of things happening, but you could summarize NEK5000 like this. Or basically any solver of CFD, probably you can summarize like this. You need to evaluate some things that you know from before. You solve an equation for pressure, then an equation for velocity, and then repeat this every time steps, right? So what does this mean? Well, the behavior actually is very similar. Once we have a flow that is fully developed, we can expect that the duration of every time step will be quite regular. And this is something that is perhaps relevant for us in Admire, if we are considering the intelligent controller or something like this. Because if we sample some time, for some time steps, it is quite likely that we are able to predict how it will behave in the following time steps. Because as I'm saying, this is always being repeating the same steps. Okay, so now I talk about the time discretization. Now, if we wanted to actually do a simulation in NEK5000, like for example here of a turbulent pipe, then it's not enough to just discretize in time. We need to discretize in space. So here's where the spectral element method comes into consideration. So we have our domain, right? And then we discretize it into a series of elements, right? These are the squares that you see here in the domain. Now remember, since we have a spectral element method, each of these elements have a bunch of points inside that come from the spectral discretization that is done locally. So yeah, then we discretize the domain. Then of course, if we want to solve the equations, and I said that NEK5000 is a purely MPI application, then the following thing to do is to actually partition these elements into multiple MPI ranks, right? So here, by different colors is different MPI ranks, and we are distributing the data. And then the way that we solve the equations is that we solve for each element individually. We solve these equations that we have for each element individually, and then at the end, we do something that it's called direct stiffness summation, where we actually average the values in the boundaries. And I'm mentioning this, I will explain a little bit more on direct stiffness summation because it's important for communication, and we are interested in this in Admire. So I will explain very briefly what direct stiffness summation does. So if we have a global domain, like for example, the pipe that I just showed, that's what I'm showing here in picture A, the global domain. Then the way that the discretization works for us is that we separate this global domain into a bunch of elements, as I was saying before. Now, if you notice here what's happening, this boundary that was shared by the 2 elements is actually present in both elements. So we are not using ghost cells or something like that. We actually have these points in each of the elements, the boundaries. Then we solve locally in each element. And then what we do to ensure continuity between the elements is that we do a gather-up operation where we basically average these values in the boundaries. And then we scatter, so we average them first, and then we set those values to be those points to have the value of the average. It's very simple. Maybe there's a lot of things happening in this slide, but just consider this. We solve the equations locally, and then we average the boundary value. That's basically it. But then the reason that I'm saying this, and that I consider that this is important for us, especially if we are caring about performance, is that, well, maybe it's very obvious, but I will state it anyway. And before I continue, I just wanted to mention this is done in NEK5000 by a library that is called ES library, that we really do not touch I mean, we developed the code NEK5000. We are developers of the code, but this particular library that does MPI operations, we don't usually get into it. We just use it. So perhaps if you are considering to modify some MPI things in NEK5000, it's probably not the best way to go. Okay, but what I said that I want to state that is very obvious is that, of course, when we are doing this direct stiffness summation, if some neighboring elements are in the same MPI rank, then of course we don't need communication. But then if the neighboring elements are not in the same MPI rank, we obviously need communication, right? We need to be able to get those values. And again, I said it was obvious, but it's important. So that's why I explicitly say it. And of course, since we are dividing the elements among ranks, then we also have the choice of try to minimize this, right? Try to minimize this effect. So the idea is that we minimize the neighbors in other ranks. Of course, we cannot only minimize the neighbors, we also need to try to keep the work balance between elements. So then this becomes basically a graph partitioning problem where we want to reduce communication, but we need to keep the load balance between MPI ranks. So there's some libraries in NEK that do this, and the way that do this, as I said, is through a graph partitioning problem. So the steps to do this are basically, we first have our global domain that I have shown multiple times now, and then we map it into a graph where each vertex is an element of the discretization, right? So then if we want to do this partitioning in a very nice way, then what we need to do, and here I'm showing an example where we want to partition a domain between two MPI ranks, right? So then what we need to do is to try to solve this graph problem, this partitioning problem, by cutting the least amount of edges between vertices. This would mean that because each edge represents some sort of communication between elements, and then if we ensure that we don't cut that many when we are dividing, then we ensure that we don't have that much communication. So as an example here, we have that in picture B, we have partitioned the domain into equal number of elements in each partition, but then we cut through 6 edges, right? While in picture D, we have done also the same partition, equal number of elements, but then we have cut 8 edges. This means that the configuration D would require more communication than configuration B, right? In NEK5000, this is done by some libraries that are called PARMETIS and PAR-RSB. And of course, the reason that I am mentioning this is because, when we are redistributing data, it's not enough to just, okay, let's do it equally among different ranks. Let's have the same number of elements among ranks. It's actually about redistributing data smartly in a way that it really will reduce communication, right? And this is important, of course, for Webminar in the context of CPU malleability, because if we are going to spawn more ranks and we need to divide the information, then we need to do it in a nice way. Of course, I know that the work packages that are in charge of this, we have, and also the co-design group, we have been thinking about it because we all know that this is a limitation that we have. So of course, as I said, NEK5000 has a library that does this, but then it would mean that an adaptation to the malleability modules wouldn't be as transparent, because then we would need to call something from NEK. But we are open, of course, to try to find solutions together. Well, now that we are talking about malleability, the question has been raised multiple times to decide where a code could be injected with malleability, like at which stage of the code we could actually maybe spawn processes or despawn them. And I would say that for NEK5000, a very obvious choice would be at the beginning or at the end of every time step. Because if you see, as I mentioned before, NEK5000 is very cyclic. We are always doing more or less the same operations. And if you go into the NEK code and you see the core, then you will see that NEK5000 is driven by a do loop. Right? So it's just cycles go from the first time step to the last time step, repeat this. Right? So I think that in this sense, it is very safe to assume that at the beginning of the time step, this would be a good place to spawn process and to reconfigure and all this. So yes, now we have been talking about malleability, so perhaps now it's time to talk about performance that I'm sure you're interested in. So here we have the performance, some scalability plots made by Offermans in 2016. These are for multiple cases, so I will briefly explain here what do we mean by these multiple cases. Here we have some Reynolds numbers that you could see it as a measure of how small the smaller structures in the turbulent field are. So as we are increasing these Reynolds numbers, then we need higher number of grid points to be able to characterize turbulence correctly. So then you see that we have four cases at 4 different Reynolds numbers, and we see how it scales. Okay. So in the pictures themselves, the dashed lines represent communication time, and the lines that have these squares represent the total time of execution for 20 time steps. It was done in this study. And as I said, even 20 time steps is very representative of how it will be for the whole simulation, because as I said, it is a cyclic operation and it is very similar. It's very homogeneous among time steps. So for the smaller case, as it would be expected at some point when we are increasing the number of nodes, note that these are number of nodes, so number of ranks is this times 32. So it is as expected as we increase the number of ranks, then the total communication time the total execution time becomes the communication time. This is expected, especially for these smaller cases. But of course, we see that for the bigger cases, as it's also expected, perhaps we have very good scalability, and we are basically linear here. And I just want to say that when we are doing production runs, when we want to actually analyze turbulence, we are most of the time actually on this side, right? These smaller cases we use probably for development and this sort of thing. But when we are actually studying turbulence itself, we want to understand what's happening, then we are at this stage, we are probably in these higher sides. We want to study bigger and bigger problems. So this study here was done in BESCO. That was a supercomputer that we used to have here at KTH. Now we have changed it. There's also some results in BGQ Mira. Again, this was also in 2016. And we see the same trends. Of course, here for the bigger case, you see that we go even to 1 million rank. The scaling here is not linear, but it's still scaling. So yeah, I think that from these pictures, you could see that NEK5000 is a code that scales very well. There's here a more recent study done in Dardel and Lumi, that are new supercomputers here in Sweden and Scandinavia. And these are a little bit of a smaller case than the other ones, or than the other big one. And we see that still scales very well. In general, there's something that we call a strong scaling limit that depends on the number of grid points per core. Not really number of elements, but number of grid points per core, depending on the order also of the elements. So that would be it about computational and CPU performance. If we want to talk about I/O, then I can safely say that we don't really do anything very fancy here. We just do MPI I/O. Each rank is writing their data into one section of a binary file. And if you actually go to the source code, then you will see that there's some wrappers here that are basically MPI file write all calls, right? So nothing fancy here. We don't really use any sort of caching or something like this that will accelerate performance, I/O performance. And regarding reading data, it is done also not fancy, very similar to writing, but since we have some partitioning codes, right? Each element knows which element each processor knows which element it should have and how many it should have, right? So at the beginning stage of when you are reading data, we read the data, and if some element is not where it should be, we can redistribute the data. And I say this because, of course, this means that we can restart our simulations with a different number of ranks than the initial run where the files were written. So this is also important, and I know that there have been some talks about this in the past regarding malleability, so we are able to do that. Now, to get into some profiling here, here we are showing some profiles that we did with a tool called Forge Map. It was a commercial software that we had in Vesco in our previous supercomputer. And this is the profile of 20 hours of execution of a case that we call the turbulent bent pipe. And this particular simulation was done with 2048 processors in 64 nodes. So you see here in green is the portion of computational activity, right, per time. In blue, we see the communications. And then in these red peaks that we see here is I/O. So from here, we see that this is quite a computational heavy application. And of course, this I/O is done at regular intervals. And this is something that we decide at the beginning of a simulation. We say, okay, I want to write data every 2,000 time steps, for example. Here in the right, I show the most used application, most used functions in the code. So here we have some functions that are used for matrix-matrix multiplications, some MPI or reduce operations that are when we are calculating some inner products in the solutions of the equations and all that. But I would say overall, the thing is, NEK5000 is quite an old code that is very well understood. So overall, there's no surprises here. We have mostly matrix-matrix multiplications and then some MPI operations. And then, of course, here we see a MPI file write all. It took 2% of the total execution time. So now you could think 2% of I/O, that's a very low number. But I would argue that because, of course, this is something that we choose, and we choose because otherwise we affect too much performance. For example, this simulation ran for 50,000 time steps. And out of those 50,000 time steps, we perform I/O in 25 time steps, right? And that took 2%. So assume that this is a linear operation, then if we want to write the data of 250 time steps, then we have 20% of the time spent in I/O, right? So this is something that we do at the moment simply because we know that we affect performance if we do too much I/O, so we just try to not do it. And also, of course, the files are usually quite big, so if we store too much, then we begin to run out of storage. So that's also something very important. If in the profiling case, we actually see the one I/O phase, then again, no surprises here. We see that the most used function in that I/O phase is, of course, MPI file write all, as would be expected. And there's some other things happening in the background too. I would say that's most of the things I wanted to show, but just to conclude, or at least to say something regarding our other problem that is not, we don't care only about I/O speed, but we care also about storage. As I said, we have a lot of time steps that we need to run, and each time step generates a lot of data. So at the moment, we are not able to store everything, not only because of performance, but because storage capacity. So we are very interested, and I say we as KTH, but also I would say very likely the CFD community is interested in finding ways to store data in a nicer way. So we have been working a little bit in compressing data, but also in analyzing data as it is produced in the simulation. So, you could say, and maybe you will argue with me on this, but you could say that a good way of doing I/O is not doing I/O. So in that sense, perhaps processing data as the simulation runs is also a good alternative to not need it to write too much. And we are doing these things at KTH in collaboration with many projects. One of them is Admire, but there's also some other projects where we have been interested in doing this, European projects, I mean. And in particular with Admire, we are working on compression, on lossy compression, because the thing about turbulence is that since it has some sort of a random nature, these lossless compressors that try to exploit some patterns sometimes struggle a lot with turbulence. So we are working on some lossy compressions, exploiting some characteristics of turbulence to compress data. So here, this is something that we have done now in the context of Admire, where we have the original data and then the compressed data that is around 10% of the original. And still we get very low errors. We basically get the same field. So hopefully on this, we will have results sort of soon that we can also show you and share with you as part of the project. But then to conclude, I would say that NEK5000 is a code that scales very well. There's definitely a lot of avenues to improve I/O performance because at the moment, as I said, there's nothing fancy there. There's also opportunities for CPU malleability, and we are interested in it. But then we need to be able to manage with the data redistribution and that the computational languages, they match and all these things. And then I would say that we are very interested in any sort of compression of data or in situ processing to manage our data in a better way. So here are some of the references that we use. And then I would also like to thank Philip Schlatter, Adam Peplinski, Ramis Orlu, Saleh, Marco Azzori, and Jonathan Vincent, and they helped me with some of these slides. So I would say that would be the end of the presentation. If you have some questions, please let me know. I couldn't see if there was something in the chat.
Hi, thank you, Adalberto. Welcome for the presentation. Has been very clarifying. I think that Mark Beck has a couple of questions, but she needs to be unmuted. Barbara, you are the...
I should be unmuted now.
Yeah, I unmuted.
Mark Beck.
Does it work? Yes.
No, yeah, it works, yes. So thank you, Alberto. It was very clarifying, and you showed the computational challenges, as well as some I/O challenges. So I'm just curious, when we are talking about I/O,
yes.
You're saying, okay, it's not a lot of runtime because you know that you cannot do a bunch of I/O because then it gets too slow. How would more I/O actually help you? Like if you could decrease the frequency that you can write out your data, would that higher resolution help you, and in what way?
In time, higher resolution in time, you mean like writing more?
Yeah.
Yeah, so the thing is that this always depends what you want to use your data for. So of course, if you want to calculate it, because turbulence, as I was saying, is a random, right? It's a little bit of a random. If you look at it in one time step, it's random, but usually we want the statistics of this. So then if we want to get nice statistics, we need to write a lot of fields, right? So then that's one particular application that if we need statistics and we don't have a way to calculate them on runtime, then we need to be writing a lot of files just to get the statistics. But also, as I was saying, it depends on the application that you want to do with your data, because there's some methods called modal decompositions that we use in Turbulent to sort of extract coherent structures from turbulence, because turbulence is random, but we want something that is coherent in there. And then for these modal decompositions, we need a lot of data. So at the moment, what we need to do is to actually run more to produce more data than just maybe have one run with a lot of data being produced. Let's say that it's sort of a compromise. And also, of course, in turbulence research, as for many other fields, there's interest in machine learning. And again, for machine learning, we need a lot of data. So in that sense, we are always wanting to print more data. We always need it because there's a lot of applications that really require a lot of data. And at the moment, we just don't do it. As simple as that. So that's why I was saying it's not only also about I/O performance, but also about compression. That's why we are so interested in compression too, because that's a big limiting factor at the moment for us.
Mm-hmm. So it could be theoretically when you would say, okay, we're using an ad hoc storage system, that you can have a lot of I/O performance, and then at the same time we could do somewhat like an asynchronous background operation from the ad hoc storage system to the parallel file system, where we do a compress operation.
Yeah, exactly. That would be magnificent. That would be the ideal case.
Okay, so I'm curious. So NEK5000, of course, can use a bunch of different workloads, right? It depends on what you actually want to calculate in the end. Are there more kind of I/O bound workloads than others?
Sorry, I missed one word. Sorry.
Are there specific workloads which are more I/O bound than others, even if it's at the same step frequency that you write?
No, I wouldn't say that. I wouldn't say that. I would say that, you know, this is something that is purely dependent on the number of grid points you have, and then you just dump that into a file. But I wouldn't say that is dependent on cases. No.
Okay, great. So
I wouldn't say that.
So if we just have any workload, for example, so some one which you gave to us, and we can just decrease the number of steps when we write, and then we show you that we can have the same kind of runtime in the end, but you can write much more frequently, this would already help you a lot.
Yes, yes.
Okay, gotcha. Very nice. Thank you. That's all that I want to know.
No problem. Thank you for the questions.
Thank you.
Okay. More questions? I have one question. As I understood, you are writing every certain number of executions to the file. Basically, you are writing because of the runtime you want to consume doing this operation, and you can restart with a different number of processes for the next execution. Is that right?
Yes, yes, it is right. It is right.
Okay. So, if you could increase the frequency of the writing, theoretically, you would like to go up to writing every execution, or what should it be your ambition? I mean, writing more?
I mean, I guess there comes a point when there's just too much data that cannot be analyzed, right? But definitely more frequent than what we can do now. Maybe to give you some exact numbers, I will need to talk with people that know more about turbulence than I know, because of course there's always some what do you call this? Some sampling theory that then we need to sample each certain time steps, and then if we sample too much, then maybe we are aliasing and that sort of stuff. So there needs to be a balance, but it's definitely more frequent than what we do right now. Right now, we really just basically don't do I/O just for some particular points. But I can come back to you with that.
Okay. Thank you.
No problem.
No more questions? No?
I think there is one question from Nafisa.
Hi, Sabat.
Hi.
Is your question?
No, it's a question from Nafisa.
There's a raised hand, but it's muted. Yeah, I see it now. So maybe if someone can unmute Nafisa.
You should be unmuted now.
You should be unmuted now. You can ask the question.
You can try to unmute yourself. You are able to do this now. Yes. It should work now. But we cannot hear you.
Maybe write it.
Can you write the question?
I see that the microphone is open, but
okay, please write your question in the chat.
Okay.
Try
to speak because we can hear the keyboard.
Speak in the microphone.
Okay, can you hear me?
Typing, probably.
Yes.
Okay, sorry, I don't know why you couldn't hear me before. So my question is, if we decrease the frequency of the I/O, what will we miss? So that what is a compromise? A compromise, I mean, there is data still, so it is in memory. So that if we have more frequency of I/O flashing, I/O checkpointing or sampling, then it decreases the memory, or just there is another compromise. So where is this data being held? So there is this data that needs to be flashed or not to be flashed.
Yeah, I mean, we have all the data in memory, and
so is your memory cheaper than your I/O? That was my question.
Yeah, the thing is that, of course, at each time step, this new data occupies the place of the data in the last time step. So we lose everything that we don't write, basically.
So if, for example, rewriting and the storage was also cheap for you, or in addition to the storage speed, that would also work for you.
Yeah, I mean, so ideally, if you could have all the information from the run, that would be good. But the thing is, at the moment, whatever we don't write is lost, because each new time step we are overwriting whatever was before. So
the ideal storage system that works similar to memory, like rewriting is cheap and also the speed is cheap, works for you too.
yeah.
Okay, that was my question. Thank you. I wanted to just be the compromise between sampling more or not sampling more. So.
Mm-hmm. Mm-hmm. Yeah, I mean, the reason we don't sample everything is simply it's too much storage, and it makes everything go slow, right? So if there were no limitations, then we could have everything, and there's no problem.
Yeah, but my question was just the rewriting and the storage as if it is a memory. So that the reason that you cannot have too much data sampled on the storage is because it consumes a lot of space on the storage.
Mm-hmm.
But
yes.
As we know, memory is more expensive. The advantage of memory is that it can be rewritten. But the storage, why not try to rewrite the storage from the previous samples? That was what I was asking.
But then, I mean, if we rewrite something that we store, then when do we post-process it? Right? Because we need all these things to actually afterwards get statistics, extract coherent structures. So we cannot really rewrite things, because otherwise we cannot really post-process it. And in the post-processing, I would say, is where the money is, right? Where then we as engineers, we analyze what's happening as researchers. So we cannot rewrite what is there, I would say.
Okay, but sorry, I'm losing you. Then you keep that data in memory instead.
No, they keep it on different versions in the disk, I understand.
Yeah, exactly.
Because they have to keep the files to make the post analysis of the data.
Yeah, exactly.
If I understand well, no?
Yeah, it is like you say, Jesus.
No, if you sample less frequent, I mean.
I don't understand. Please,
Yeah,
maybe you can contact Adalberto.
Yeah, exactly.
Okay.
He can explain it to you.
Yeah. I was just meaning, where do you keep this intermediate data if you are not keeping it on storage?
I mean, it's gone.
Okay.
I
mean, maybe we need to talk.
Okay, I will contact you.
Yeah, exactly. Let's talk.
Thank you.
Yeah.
More questions? Okay, so with this, thank you, Alberto. We finished this presentation for NEK5000, and we are closing the recording of the session. Thank you, everybody, for attending, and thank you again, Alberto, for the nice presentation. Okay.
Thank you very much. Thank you for your questions.
Thank you.